In this work, we present our online dynamic motion planning and control framework for wheeled biped robots' hybrid motion generation. Wheeled robots are faster and more efficient comparing to legged robots. However, legged robots are more capable in terms of traversing challenging terrains. Wheeled legged robots combine both advantages of the wheeled robots and the legged robots. Hybrid locomotion has been demonstrated on wheeled quadruped robots but rarely on wheeled biped robots. This motivates us to study the motion planning and control of the hybrid locomotion of wheeled biped robots. We propose to combine the cart linear inverted pendulum model and the under-actuated linear inverted pendulum model to generate hybrid motion. To the best of our knowledge, we are the first to apply the cart linear inverted pendulum model for rolling motion generation. Start with the modeling. The hybrid motion has been decoupled into rolling motion in sagittal plane and walking motion in frontal plane. For the rolling motion, the cart linear inverted pendulum model has been proposed to capture the essential part of it. The under-actuated linear inverted pendulum model is used to generate the walking motion. These two models are both based on the standard linear inverted pendulum model. The essential difference between them is the type of contact. The cart linear inverted pendulum maintains its contact with the ground since the wheel can rotate continuously. For walking motion, the contact updates discretely. As can be seen here, the dynamics of the two models take the same form. Note that xp, the wheel contact point in rolling direction, can change continuously, however, yp, the contact point in lateral direction, can only change discretely. The dynamics of the cart linear inverted pendulum model can be rewritten in state space form as shown here. The state includes the position and velocity of the center of mass and the contact point. The input is the acceleration of the contact point, more accurately, the linear acceleration of the wheel center point. It is a linear time invariant system. We can apply a linear quadratic regulator to stabilize the system. The cost term associated with LQR includes two terms, desired velocity tracking and wheel acceleration penalization. The feedback law that minimize the costs can be figured out accordingly. The calculated wheel acceleration will be sent to the whole body controller to track in the next control layer. For the walking motion, we use the under-actuated linear inverted pendulum model. The contact of the model updates discretely, assuming fixed foot contact location yp and given the initial center of mass state. The evolution of the system dynamics is fully determined and the analytical solution can be also figured out. In current support phase, the robot is basically falling over passively, that's why we call it underactuated. However, we can still update the contact location discretely to shape the system dynamics periodically. The walking motion planning problem becomes a footstep planning problem. The optimization variable is the next n footstep locations. The goal of the footstep optimization is to track the desired center of mass velocity while regulating footstep length. The discrete system dynamics is enforced as the constraints to guarantee the feasibility of the optimized footstep locations. At the end, the center of mass trajectory can be figured out from the optimized footstep locations. Previously, we have introduced how the hybrid motion can be decoupled and how each decoupled motion is planned. To realize these planned motion on the robot, other pieces are needed. Here we introduce the whole control framework. It has a layered structure. From the top, the inputs of the motion planner are the contact sequence automatically generated from the state machine and the desired velocity provided by the user. The motion planner outputs all Cartesian space targets such as center of mass and end effector targets. The targets will be sent to the whole body controller to track. At the end, the whole body controller outputs all joint torques and send to the robot. Last but not least, the state estimator collects all sensor data and estimate the state of the robot for next control loop calculation. Here, we show some simulation results to verify the proposed control framework. As shown here, the rolling motion has been tested first. A constant desired velocity command has been sent to the robot. It starts from stationary configuration, it rolls its wheels back first to accelerate and then gradually converge to the desired velocity. The behavior can be tuned to be more gentle or aggressive by tweaking the LQR gains. Another basic mode is walking. The desired velocity given in the lateral direction is 0. The robot changes its contact between the feet periodically. In fact, we have designed a 2-degree of freedom angle joint to enable the decoupling of rolling motion and walking motion, which is different from most existing wheeled-legged robots with only a single degree of freedom angle joint. At the end, we have designed 2 scenarios to highlight the bipedal hybrid locomotion. In the first scenario, an obstacle is presented in front of the robot is able to step over it while the other wheel on the ground keeps rolling. In the second scenario, a much higher barrier is placed in front of the robot. Instead of steering away to move around it, with the hybrid mode, the robot can step aside while rolling forward.